And the timer is starting now. So Kwaku, you're good. Take it away.
Thank you for coming by to listen to this presentation. The presentation, in terms of my research work, is Quarry raw material optimization and CO2 sensitivity and predictive analysis in cement manufacturing. So I'll just move ahead. And the research work is divided into two aspects. Part of it is phase one, the first part of it, which is cement quarry material optimization. And the key questions that we want to answer is that how can kiln feed chemistry, overburden wasting, and reduction in sand usage be improved by optimizing quarry material mix? The second aspect of that research is also phase two, which is CO2 sensitivity analysis and predictive analytics of calcination process. Whilst I'm giving the presentation, I'll go into details regarding these terms. The presentation outline or my talk will be, I'll give a general overview of cement and concrete manufacturing and why we need cement and concrete. Then I'll talk about problem statements. My problem statements will be related to the phase one and phase two. Then I'll talk about methodology that has been adopted in terms of this research work. Then I'll give an update on results. The result will be on only phase one because that work has been completed and published. Then we'll talk about the conclusion. What is the general overview of cement and concrete? So population has grown since 1900s, 2000s, population has grown, just as we see in these graphics. Population has grown because of urbanization also has grown. Because of this, there's a demand for cement. The second aspect of this PowerPoint, you can see the demand of cement. As the trend shows, cement has been increasing over the years. And you can see that cement has, as compared to other construction materials like steel and wood, the demand of cement has increased. Also, on the same chart on your right side, you can see the trend of projection in terms of projection of cement demand to 2050, which shows a trend of high increase, and it's because of urbanization and also growth of the economy. Why is it that cement is so much required? The text slide shows this. Cement is used in concrete. So every infrastructure that you see around, cement is used in concrete. What is concrete? Concrete is a mixture composite of cement, which is ranging between 7 to 15%. It has some air in it and 14 to 21% of water. What we add to it is aggregate. And the aggregate is added and it is mixed together to get a concrete. Now, the reason for using cement is because of the compressive strength of it. The compressive strength of it is high for infrastructures. Also, we add rebars or metal bars or fibers into it to help in terms of the tensile strength of it. So the picture on your right, on your screens, the upper one shows concrete, which is a mixture of the components. So when we go to Walmart and we buy a cement, cement is a powdered form. It looks gray. That is just cement. Concrete is the final product used in infrastructure. And the cements serve as a binder between these materials. There is the clear facts. These are the clear facts. Cement is an integral part of concrete, which is end use into infrastructures, which is needed. Cement production in the United States has reached an estimate of about 92 million metric tons in 2021. The whole world is about 4.4 billion metric tons. And therefore, it means that cement is needed. We have no option, but we need cement. And also, but the question still remains, how is cement manufactured and what are some of the environmental issues related to cement manufacturing? And how can we improve the environmental impact of cement manufacturing using system engineering methodologies? How is cement manufactured? In cement manufacturing, there's a series of phases that the manufacturing process goes through. We start by first getting the raw material. Now, raw material, 90% of that raw material comes from the ground, which is limestone. The reason why limestone is more suitable is because of calcium carbonate. Limestone is made out of calcium carbonate. Even with that, there's a percentage of calcium carbonate with less impurity that is required. If you look out on the screen, the limestone, the first part of it is the limestone, which is this. The limestone is, we obtain it through quarrying. After that, we add some addictive to it because of the chemistry content that we need. We add aluminum, we add iron, and we add silicate. The silica comes from sand. We add all of them and blend it, and we run it through a process called calcination. And the calcination process, we drive a lot of heat through it. And because of the heat, we change calcium carbonate into calcium oxide and CO2. And then the process of calcination continues within the kiln, which is, the kiln is also a high heat zone, about 1400 Fahrenheit heat zone. Within the process of heating it, it changes in chemistry. And when it changes into chemistry, the limestone with the combination of aluminum, iron, and silica becomes a silicate product called clinker. The clinker is cooled down because of the amount of heat involved. When it is cooled down, we run through a system called finish grinding. When the clinker comes out, it is so much in an aggregate form, and therefore we have to powder it into pulverize. To pulverize it, we have to use either a finish mill, vertical mill, or a ball mill. And then we run it with that with gypsum. The reason why we add gypsum is the setting of the cement. So the end product in bags or bulk ends up in the marketplace where it is used for concrete. The first aspect of that research work, we already know that we're talking about that the raw material that we obtain is from limestone. If you look at this is the pit. This is a similar pit where we obtain limestone for the manufacturing, which is about 90% of our raw material. And this shows the cement manufacturing factory. Now, if you look at this presentation, there's an impact. When even the first scene that you see over here, there's a big hole. We make a big hole in the ground to be able to obtain that limestone as 90% of our raw material. The other aspect of it is that, you remember I also mentioned that we use sand as an additive to it to be able to manufacture cement. The sand is mostly imported. We do not manufacture cement, we do not obtain sand at the zone of the plant. We always import it. So it has a social impact. If you read most of the articles in most developing countries, there's mafias involved in sand winning. We win sand along sea coast, destroying the environment of it. Then the material that we get out of the quarry, some of it is also dumped as waste because we cannot use everything. So because we cannot use the whole 10% of it into the process, we dump it as waste. So we create waste stockpiles. Unfortunately, some of these waste dumps, when it rains, it creates water contamination. So we create that. Those are some of the environmental impact that is created because of the waste dumps that are created from the mining of the limestone. Upper here shows the content of material that is used for the manufacturing of sand. Just for the manufacturing of cement, just as I've already mentioned, we have 80, some places, some plants uses 80% of limestone, some uses 90% of, based on the enrichment of that limestone. But there's iron, there's sand, fly ash, and pounded ash. Most of these additives are all imported and they have an impact. Now, we adopted this methodology. The methodology that we adopted was that what we are going to do is that we will plan the quarry to its perfect optimized shape. And one of the things that we did was we used a software. In mining, most of the softwares that are designed for mining of iron and gold. So we needed to modify that software to be able to be used for the limestone cement because it is totally different. In gold and copper, they look at grade in terms of grams per ton. In cement, it is chemistry related and it is a lot of blending. It requires a lot of blending. So we had to modify the software. So we modified the software. What we also did was that we created a data loop feed system loop where the data is collected and there was a closed loop for us to see whether we can control chemistry of the material that is used from the quarry. We developed that one also as a methodology. Then what we also did was that we created a visualization system for our operators to be able to see the actual impact of quality so that we can adjust and make sure we do not overmine. So these were some of the methodologies that were adopted. Out of that, we were able to write a paper on it, and that paper has been is now in press in a journal right now that is going to be published. I work with Dr. Smith on this, and it is being published. 3 minutes to go. On the second aspect of my research work, which is the CO2, is the second phase of the manufacturing. When we manufacture, you remember I mentioned that when we apply heat through the limestone, we do generate CO2. Currently, cement manufacturing companies are under a lot of stress, and because they are under a lot of stress because of their emission of CO2. So how do we understand the mechanism of this? First, when we get the material from the limestone, what we do is that we crush it into -5. We publish it into fine, and then when we publish it with fine in the raw mix, we send it through a system called the preheat tower. The preheat tower is the first stage of calcination. When we calcinate it within this system, we generate what is the CO2 through the tower. Then when we finish this, we do it again the second time. We also apply more heat through the kiln to be able to let the chemical reaction take place to create the clinker. And whilst we are doing calcination within the kiln also, we generate a lot of CO2 to the surface. Now, this is where my second phase of my research work is involved. The question is that what is the mechanisms that takes place in terms of the calcination within these zones? And what are the impacts? What are the variables that impact this? And we want to understand this by using machine learning. And just as I've said, the problem statement is that the construction industry contribute nearly 11% into the CO2 emissions. Out of that, 8% is cement manufacturing. It's related to cement manufacturing. And we do believe that if we are able to use machine learning to understand what is the mechanism and what are the critical variables that affects this emission, we'll be able to improve the system in terms of efficiency and reduce our CO2 emission. And that is what we are working on. We'll be using our methodology that we are adopting is based on collecting a lot of data. Now, in cement manufacturing, we already collect a lot of historical data based on monitoring the performance of manufacturing. And this data is already collected historically. Unfortunately, nobody has ever used this data in terms of improving the CO2 emission. So we are going to use that data, make sure that we use historical data, run sensitivity analysis to see which variables affect what variables, and be able to use predictive analysis to be able to see whether we can predict the CO2 out of the manufacturing process. We have already published a paper through a conference already on this, SME, which is a mining conference. So we will continue to work on this. I just wanted to say that this project is part of a super project, cement and concrete research work that we are doing. Part of it is my work, which is the raw material optimization and CO2 emission. We are also looking at efficiency improvement in terms of power usage, because power also influences CO2. We are working on that using machine learning. Then a colleague of our team is also working on carbon capture in an end-use product, which is the concrete. Can we capture CO2 in concrete? The team members is Dr. Steve Simsky, who is our professor leading researcher, then Dow, myself, and Kevin and Timmy, who are part of that research work. That is all that I have. Any questions? Thank you for listening.
So we have about 6 minutes for questions.
Hi. Should I raise my hand or
Go ahead, Dawn.
Go ahead.
Yeah.
Yeah, I just wanted to say excellent presentation, Kwaku. I really enjoyed hearing that. And my main question was, so I understand that there's a lot of work being done with optimizing the various components of cement manufacturing. What types of machine learning or deep learning algorithms have you looked into that you might actually employ for this? And is there, and can you go into a little more detail on how artificial intelligence will be employed here?
So currently we are looking at regression analysis, using regression analysis. And we have what we are going to do is that we know that we have so much data, historic data, but based on we have the dependent and non-dependent variables. So what we are going to do is that we'll start first by understanding what is the impact, the most common non-dependent variables that affects our CO2, which is our dependent variable, rate them based on regression analysis. Then from that, we'll be able to predict. For what we are going to use for machine learning in terms of predictive analysis, we haven't chosen yet. Three of us we are a team right now looking at the options that we have in terms of which kind of machine learning analysis that we'll be doing, predictive analysis that we'll be doing.
Brian Wilson, really enjoyed the talk. Came in a bit late, but I really wish that I'd seen the first part of that. Two questions. The SUPPER consortium, what organizations are part of that? And then I have a follow-up. I'll ask after that.
Sorry, with which organization is involved? The only organization that is involved right now with that group is my own company, which is Lehigh Hansen, and then Colorado School of Mines. I've got my company involved in terms of using our lab work, our lab company, to do some analysis for us internally. So it's only two of us that are involved.
The other question was on, there is a lot of, we're doing a lot of work on hydrogen, and there's a lot of interest sort of globally on utilization of hydrogen in cement production. I wonder if that is something that enters at all into the type of work that you're considering.
No, we haven't. So just for my clarification, when you talk about hydrogen, are you talking about hydrogen in terms of generation of power, or
but in terms of industrial end uses, two big uses that are being considered in the long term are for using hydrogen in refineries, in steel manufacturing, and in cement manufacturing.
We haven't looked at that. Okay. Thank you.
Okay, thank you. Thanks.
I have a question, but this just might be from I don't have a lot of information on this topic. Are there any other options besides limestone? Like, are there any, man-made materials people are looking into, or not really?
Excellent question. Excellent question. This has been one of the most challenging questions for us, because limestone CO2, we cannot avoid that, right? So currently, there are other companies looking at clay, whether we can substitute limestone with clay in the manufacturing of cement. It's questionable, but we are still looking at that too, yes.
I have a question. If there are other students who are interested in joining the super project, what would you tell them in terms of furthering their interests or joining the project?
I think what I'll say is that this is the future. Mm-hmm. There's a lot of scrutiny about cement manufacturing and in terms of its CO2 and environmental impact. So if you have a skill set to be able to help us as to be part of the team, that would be great, but it has to go through Dr. Simsky.
Mm, excellent. Thank you.
Are there any other questions for Kwaku? If not, if you do think of a question that you didn't get a chance to ask, feel free to send it in a chat to Kwaku, or we can share contact information after as well. But great job. I wish that everyone could give you an actual applause. So that was really great.
Thank you very much.
Okay, Mac, I think I have made you co-host, so you should be able to share your screen. There we go.
See my screen?
Yep, it looks great. Let me get the timer started for you. And you're good to go.
All right, thank you. Well, welcome everybody. Thanks for attending. Kwaku, you've given me a lot to think about because I'm in the beginning of my research, and it's in terms of having a hypothesis, statement of a problem, methods I'm going to use. That's still pretty early. But what I'm going to talk to you guys about today is the next generation spacesuit development. It's going to be a case study on systems engineering best practices. My name is Michael Cabrera. Everybody calls me Mac, and I'm a project manager for a NASA contractor. So when it comes to next generation spacesuit development, I've been at the forefront. So what are we going to talk about today? I'm going to give you guys an introduction as to where I'm at in the research right now. I'll give you an overview on the next generation spacesuit, and then I'll go over kind of the general dissertation review, what I'm thinking I'm going to review in terms of case studies. So introduction, right now, what my company, I see a sidebar on the side. Do you guys see that? Or can you see the full presentation?
I see the full presentation.
Okay, great. Okay. So I work for Jacobs, who's a NASA contractor, and we've been developing the next generation spacesuit for NASA, and we're doing it against a radically different level of customer expectation. So essentially what happened was we were developing a new generation spacesuit, and the administration in 2019 said, we want to go back to the moon. So the new spacesuit we were working on was for the ISS. So now we got to make one that's for the moon. Well, now you're changing the system context, you're changing the requirements, and now you're accelerating the schedule. And what ended up happening was that there was a lot of budget and schedule overruns, and eventually the work is getting sent to a commercial partner pretty soon. So I thought this would be a great time to capture some lessons learned, but also I see some case studies here. And what can we do to qualitatively and quantitatively analyze some of these things where systems engineering practices could have been optimized, and how could we have met cost, scope, and budget? So while I don't have a hypothesis of something testable at the moment, or a very good, clear, I guess, statement of the problem, I do know that there are things that we could have done better, and they come back to systems engineering best practices. So what we have is an EMU. You're going to see a lot of acronyms. EMU is an extravehicular mobility unit. The last time we had one of these that was designed was in 1984. So we have a lot of things that need to be improved. The spacesuits that we currently have are very, very heavy, and we need something with more points of articulation. There needs to be a little bit more ease in mobility. And also this new suit lacks the ability to sustain lunar missions. One of the big things that this means is they need to be compatible with lunar dust, or what we call regolith. So what exactly do we need to develop? Well, the XEMU, which is the new spacesuit, exploratory extravehicular mobility unit, is going to be the next generation spacesuit. And you got three complementary systems. You have the exploratory portable life support system, which maintains life support functions. That means you got to keep the crew, you got to keep ventilation, you got to keep oxygen pumping through the suit, and you got to keep thermal properties, which mean you got to keep the astronaut cool or heated depending on the circumstance. You have a pressurized garment, which is actually the suit itself. So if the XPLSS is the backpack, right, that supports life support, the pressure garment is like the big suit itself. And then you have the XInfo, the exploratory informatics system, which is the telecommunications and the data processing for the entire XCMU. This is the radio, this is the antenna, this will be the lights. And the hallmark of the system is the ability to interface with lunar dust and sustain the longer term EVAs. So the EVAs we have now are going to be limited in terms of what you can do on the ISS, supporting operations around the ISS. But if you're going to be on the lunar surface, you're going to need to have extended EVAs, and these are a vast improvement over the Apollo. So one of the questions is, we've already been to the moon, we've already had EVAs. Well, these are going to be able to sustain longer EVAs, and they're going to be able to. We had a lot of lunar dust problems on Apollo. So how do we mitigate that now? How do we make a suit that is what they call dust tolerant? Can it be cleaned easily? Can you design it to be more dust tolerant meaning dust doesn't get in crevices, things of that nature. So I'm seeing right now what the big issue or the big challenge on the project has been when it comes to requirements engineering. So when we talk about systems engineering best practices, for me, it all comes back down to requirements engineering. And I think the hallmark, of course, is going to be lunar dust. There's several different case studies when it comes to requirements engineering, but effectively, you have 200 system level requirements. You change 50 of them, you add 16, you delete 7, and you think, well, you've changed about a third. So the other 2/3, you got to be pretty close to where the seat was needed to be ready for the moon. Well, not quite, because below the system requirements, you have the subsystem requirements, which is 3 primary subsystems we talked about, were the informatics, the portable life support system, and the garment itself. But when you change the system requirements at the top, those trickle down to the subsystem, those trickle down to the component, and those trickle down to the unit. And now you're talking thousands of pounds, thousands of requirements that were changed. So working as a project manager and also working in a more technical capacity when it comes to verifications and validations, where the verifications written correctly, is the customer able to validate the hardware? And one of the case studies I take is lunar dust. One of the things that's very interesting when it comes to lunar dust is we don't have a lot of metrics as it pertains to the regolith. Can we create a simulant? How do we test it? How do we know that we're testing it correctly? So we ran into a lot of issues, and to keep it very high level, long story short, it was very hard to write these verifications, and it was very hard to write these requirements, basically because of the way that they were decomposed. And I think if I was to make a hypothesis, or the problem was, the hypothesis is, if maybe we had written these per and COSI standards, if we had made use case scenarios, state machine diagrams, if we had written a concept of operations that was more conducive to the actual work that was going on, maybe that would help the requirements develop a little bit better, because at the end right now, we are struggling to meet this, I wouldn't call it a basic requirement, but the hallmark requirement. So this comes back down to an examination of model-based systems engineering. Did we do our diagramming correctly? We have to characterize it against something. We're to characterize it against COSI standards. Were they written correctly? Are they verifiable? Can the customer validate them? Do we clearly capture the scope? Are they written by people that are doing the work? And I think for me, the purpose is going to be to understand the challenge. Can we qualitatively and quantitatively define it? And then how can we compare it against alternative methods? And if we can be able to test these methods, right, if it's someone else can produce and replicate what we've done, characterizing against a standard, can we be able to deliver this correctly? So this would be looking at the work that was done, applying different standards, or applying the standards by COSI, applying alternative methods, and be able to characterize how we could have met this requirement a little bit more clear. The next development for me is working with my team specifically. So I work with a testing team. Effectively, what we do is we take components that are on the portable life support system, we put them in a vacuum chamber, and we run them through a series of tests. Now we're talking verifications and validations. Long story short, we ran over cost, we ran over schedule, and it was very hard for us to develop this testing. And I think a lot of it comes back down to verifications and validations. So it's very easy to say, well, we're over budget, we're over schedule, we could have done it differently if we had done something else. Well, that's more descriptive. How do we define that? So I was able to characterize, well, here is the earned value metrics. You got cost performance indices, you got schedule performance indices, and we worked in a waterfall environment. I think for me, one of the bigger challenges, how do you deliver value immediately? Running Scrum and running Agile is something you hear very commonly, but I think one of the major challenges is, well, those things are good, but are you applying them correctly? Don't just apply them because you hear that this is a good way to iteratively and incrementally deliver value. You're going to have to do this in a way that is reasonable, and you can apply an appropriate method. So one of the things that I did was I quantified, well, here's our earned value metrics. And then I was able to say, well, how could we transition this team to more agile developed team? so we can deliver value right away. We had very long stints between verifications and validations of the hardware. How could we run sprints, for example, for hardware sensitive projects instead of the more familiar software intensive systems that Scrum is more attuned for? So what is the purpose? Once again, understand the challenge, why it happened, and what are some of the best practices in terms of systems engineering, whether it's something like could an agile methodology been applied? Should we have done our verifications and validations a little bit differently? How could we have developed earned value metrics? Did we do risk management correctly? So we can characterize the work that was done, and we can describe perhaps an alternative method, but more importantly, can we provide a method and is it testable, right? Are we able to show that, well, here's the performance, here's how the performance could have improved if we had applied these standards a little bit differently or taken a different approach. And that's more for the testing team, which once again ties back into the verifications and validations when systems requirements, when requirements engineering has gone through the full gamut. So right now, very early on in the research, the project is coming to a close. So I found this to be a very good point to do a lessons learned, gather information, but most importantly, how can future contractors benefit from this information? So that's all I have in terms of the research I've done. I open the floor to questions.
Hey, this is Danny Call. I had a quick question for you. So you mentioned in that part of the problems was, perhaps the MBSE wasn't utilized properly or the diagrams weren't created properly. Were you saying that it wasn't done right or that it wasn't done at all, and that using more MBSE could have helped more in that project?
Right. So that's a good question, because that's a few questions in one. So when it comes to MBSE, there were 3 subsystems. 2 of the subsystems followed MBSE pretty closely when it came to, we use Cradle, right? As this is the repository for requirements. So the idea is that you put the requirements in an MBSE tool like Cradle. That's one of the 3 pillars of MBSE. And then you are able to push those very systematically to develop documents, right? And this is to populate documents across the whole spectrum of the document database. That way you save time and you don't add a lot of extra work. Where one of the subsystems already existed, so they did not use the MBSE tool as intended. And one of the case studies I do look into is, well, what they did was they had documents, and instead of putting the requirements into an MBSE tool to spit out the documents, they did more of a document-based system engineering, where they had documents that already existed that were legacy documents from 10, 15 years ago, and they fed those directly into Cradle, meaning you take the you go backwards, you take the document, you strip the requirements, and you populate it. And one of the things I found myself was trying to steer narrative. Well, this was not the best way to do it. Now you've introduced problems. That wasn't really the case. Not every group needed to follow the same standards, especially if something was well developed. So that was one case. Another case is the concept of operations. So in some cases, especially when it comes to lunar dust, I found right now in my research, I find that some areas are lacking. So did they have a good, did they have scenarios and goals listed very clearly? Did they have a main, did the main, exception, alternative scenarios listed? And in some cases they do. And in some cases, the concept of operations, I would still say needs to be developed, whether that's using like a use case. And as rudimentary as that sounds, if you start at a very high level, we need a suit. We need the suit to be dust tolerant. And then you start creating goals around that. You can find that some of the redundancies in your requirements can be reduced if you start pruning that requirements tree. So I guess to answer your questions, one of them was a look at how MBSE was used in terms of, was it used correctly? And then another one of the case studies is, once you have your requirements developed, were they done against good diagramming? And one of the things that I started developing was, how could have use cases been developed a little more adequately, because those weren't done against Nkosi. Not to say that that's incorrect, right? But it is interesting to find that if you were to follow the standards, maybe that could have removed some of the redundancy, and you never want to have redundancy when it comes to requirements. You want them to be atomic. And a lot of the time I found that across the board, you might have had requirements that were duplicated or that were not atomic. Did I answer your question?
Yeah, thank you. And maybe just a little follow-up. With the desire to use MBSE, was there a mandate to do that, or was that just a decision that the systems engineering team was left to make as to how they wanted to approach, document-based versus model-based?
So the first subsystem had been developed since 2007. So when the other two subsystems joined to create the next generation spacesuit, there wasn't a strict mandate, but there was this is what the other systems follow, or is the third subsystem going to comply? And I guess the answer would be no. I don't know at what point was there more of a formal, like this is what we're going to use, but whenever the systems engineering and integration branch developed, the idea was that we were going to use this MBSE method across all three subsystems. And what effectively happened was that there was a decision made that, well, the requirements had already been decomposed in one subsystem. All we need to do is make sure that they're compatible with the system requirements above them, which at first glance sounds problematic. It sounds disjointed, but I guess to answer your question, there was never a formal mandate of you need to follow this. It was more of a recognition of, well, is it worth the time to start over, or can we not follow the standard that the other three subsystems are doing, and will that be an issue? And right now I'm not finding any. You would imagine that there would be a lot of issues with, well, now we're not following the other standards that the other subsystems are doing. How do we not have parent-child disagreements? But by and large, surprisingly so, that the decision not to follow I do not find any evidence right now that I can quantitatively or qualitatively state that it created a lot of problems across the board.
Great, thank you, appreciate it.
Other questions for Mac?
Yeah, this is Jim Adams. I came in a little late, but I like that at the end, the focus was on one of your lessons learned was, can we be more agile about this? In testing programs, it's interesting to ask the agile question, because we usually have this big list of things we want to test to certify, which then becomes the requirement. You can't avoid it. But if we're trying to learn, then we're really testing for information, and that's more of risk. It's really burning down risk, the risk of things we don't know. Did you have a kind of a backlog list of what's the most important thing we need to learn first?
Well, I think, when you say the most important thing to learn first, do you mean in terms of like agile methods, or
no, the equipment, the spacesuit? Yeah, because you were doing a lot of testing, right? They were testing the suit and
yeah.
And yeah.
Well, I think one of the things that we really struggle with is you run into a problem with schedule where when you're thinking of systems engineering, you're supposed to be doing your unit tests first, and then you do your subsystem, and then you do your system testing. So one of the things that we learned is that a lot of the time you can make assumptions on how equipment works at the unit level, but then there's emergent behavior that occurs when you start to mix systems. So the biggest struggle was, how do we, it all comes back to interfacing. We have a ton of different contractors and subcontractors. And I was actually in the lab yesterday, and you start hooking up the system and you think, well, we've already done all the unit testing. Why is the system or the subsystem not working now? And what is some of the emergent behavior? And a lot of it comes back down to the assumptions you made at the unit level. So if we're using a controller to commutate to a pump, and we used some kind of controller that was developed in-house instead of the actual controller that we should have used, there's a whole plethora of now electrical issues that you just curtailed around. So anytime you can breadboard with actual hardware that you're going to use. So I think that was one of the biggest problems that surfaced right away, is Yeah, it's easy to do these units, subsystems and system testing, but what is the emergent behavior when you start combining these items? And that's something that we're still struggling to answer.
Yeah, I might even have rephrased it as it's easy to plan for testing.
Yes.
Right, based on chalkboards and drawings and even models, but that emergent behavior has to be reckoned with. And I do think agile test planning or test execution could help to absorb some of that, because you can immediately say, if you know your burn down plan in agile, you'd say, oh, we just discovered, some extra scope that we need to deal with, and it's risen to the top of our list, so we're going to burn that down first.
Right.
That would be it would be recognized that these things always show up and we need to be prepared for them. But it would also make you think ahead. What's the risk that we're going to discover these things? And then maybe the risk is so great that the testing needs to start earlier, or we need to have a different way of planning and executing it.
Yep.
Hey, great stuff.
Thank you. I appreciate it.
Good job.
Thanks, everybody. Appreciate it.
All right, Danny, it looks like you already beat me to it. So let me stop the timer and restart it, and you're good to go.
All right, let me get set up here. So as you can see, I'm taking the distance learning to the next level. I am out in the great outdoors today, so hopefully my connection is stable enough to get by. But I'd like to talk to you a little bit about what I've got going on with my research into the application of the diffusion of innovations theory to the adoption of model-based systems engineering. And just quickly, by way of introduction, Danny Call. I did my undergraduate degree from BYU in mechanical engineering, and I have completed a master's degree in systems engineering from the Naval Postgraduate School. And I started the PhD program here at CSU back in the fall of 2020. So I'm finishing up the last of my coursework this semester and really getting going with my dissertation now. And I'm being advised by Dr. Herber. Work-wise, I am a civilian engineer for the Air Force. I spent the first couple of years of my career down in the desert at Edwards Air Force Base at the then Air Force Flight Test Center, working on weapons integration on F-22, F-16. And since then, I've been at Hill Air Force Base in the software engineering group, working on a variety of platforms, F-22, F-16, A-10, F-35, and loving it. And lucky that the Air Force has given me the opportunity to pursue this educational opportunity. So I'll dive right in. Systems engineering is an inherently interdisciplinary discipline. So as systems engineers, we're responsible for developing, managing, and integrating systems engineering data. And we capture that data in documents, spreadsheets, figures, and other products that are exchanged amongst the stakeholders. Now, traditionally, this has been done, as you see here on the screen, point to point, sharing documents amongst those stakeholders that I talked about. Over the last 20 years, we've been moving to a model-based approach where instead of sending documents back and forth, all of that systems engineering data is stored in a shared model that all the stakeholders have access to. And we reduce the number of dependencies between the stakeholders and between those documents. And this is what has been referred to come to be known as model-based systems engineering. And NCOSE in the Systems Engineering Handbook has defined MBSE as the formalized application of modeling to support system requirements, design, analysis, verification, and validation activities, beginning in the conceptual design phase and continuing throughout development and later life cycle phases. So it really is supporting the whole life cycle and the formal application of models. Really, a drawing on a paper is in a way a model, but we want to be more formal, and that's what MBSE is. Now, personally, I was first introduced to MBSE in my master's degree at the Naval Postgraduate School, got really excited about it, and then wondered, why have I not seen this before? And as I go back to work and with the programs that I'm involved with, I wasn't seeing MBSE being used. And so I started to wonder why. Model-based systems engineering seems like the better way to do it. There's a great deal of literature out there that demonstrates the advantages of MBSE and what it can do for programs, but it's not being used widely, at least in my sector. So I wanted to figure out why. And quite frankly, MBSE solves engineering problems, but the problem of it being adopted isn't necessarily an engineering problem in and of itself. So Michael Griffin, a former NASA administrator and Undersecretary of Defense for Research and Engineering, had this to say. Until and unless we begin to delve into the social and cognitive aspects of how engineers work together and how systems engineering is performed, possible contributions from fields far apart from engineering will continue to go unrecognized. The study of human interactions, cognitive psychology, social choice theory, and other disciplines must be included in the development of effective theories of systems engineering. And so this inspired me to look outside of strictly engineering disciplines to understand why model-based systems engineering is not being used as widely as you would think based on its benefits. So one of those fields that I've looked at is the diffusion of innovations. This was developed by a sociologist named Everett Rogers, and he wanted to understand why some agricultural innovations were adopted rapidly and widely, while others with similar benefits were adopted more slowly or not at all. And he wrote his first edition of Diffusion of Innovations back in 1962 and continued to develop and refine it, publishing a fifth edition as recently as 2003. Now, he observed that no innovation is adopted instantaneously, no matter how good it is, that every adoption or every innovation follows some kind of an S curve, where you have early adopters that get on board early, and then there's an early majority, late majority, and laggards before it levels out. So this S curve is followed by any group that adopts an innovation. Now, this is generalized. For some innovations, this process happens within a matter of weeks, like a viral video on YouTube. For other innovations, the process can take years or even decades, as we're seeing with model-based systems engineering. Also, the total percentage of adoption varies. There are some innovations that are only going to be adopted by a small niche of users, while others are widely adopted, but they all follow this generalized S curve. And to understand the variables that affect how fast this curve goes and how high it goes, Rogers identified 5 variables. First, the perceived attributes of the innovation itself, the type of decision that goes into deciding whether or not to adopt, the communication channels that are used to spread information and knowledge about that innovation, the nature of the social system that's considering adoption, and finally, the extent of any change agent's promotion efforts. Now, obviously, all 5 of these contribute, but he realized that depending on the innovation, 49 to 87% of the variability in adoption rate could be attributed to the perceived attributes of innovation. So that's where I've decided to begin my research on this. So first of all, the relative advantage is the most straightforward to understand. It's simply the degree to which an innovation is perceived as being better than the idea that it supersedes. And this can be measured in economic performance, prestige, and so forth. It also explains slower adoption rate for preventative innovations like a seatbelt, because you don't see that advantage because the result of the innovation, the advantage is a non-event, like not being seriously injured or killed in a car accident. The next is a compatibility, or the degree to which an innovation is perceived as consistent with existing values, past experiences, and needs of potential adopters. Organizations generally can do a good job studying an issue out, but as individuals, we typically make decisions based on our own mental models, what we already understand. So if an innovation is more compatible with those existing mental models, we're more likely to adopt it. And also, if it meets a relative need, we're more likely to adopt. So complexity, again, just a degree to which an innovation is perceived as relatively difficult to understand and use. If it's an iPhone that you can just pick up and use, you're going to adopt it a lot faster than something that requires specialized training. Trialability, the ability to experiment with that innovation on a limited basis prior to making your decision. So innovations with a high cost of entry are adopted slower because you have to make some kind of decision before diving into it. So if you have the opportunity to try it out before you buy it, so to speak, you're more likely to adopt. And finally, observability, just the degree to which results of an innovation are visible to others. So for physical innovations that like produce a very demonstrable product, those are more likely to be adopted than more procedure or knowledge-based innovations that take some kind of domain knowledge to really appreciate what that innovation is doing for you. So what I would like to do now is look at MBSE through the lens of the diffusion of innovation theory and how does it stack up? So first of all, with relative advantage, the current perception of the relative advantage of MBSE is hurt because there is an upfront cost. So people, potential adopters, see that there's an advantage, but because of the early upfront cost, and I've got kind of a normalized graph here of systems engineering lifecycle cost, that spike in the beginning due to purchasing new tools, training people on new tools, languages, and processes actually do make it more expensive. Even though that's made up with savings later on, that does hurt its initial relative advantage. And also with the current perception, it's a preventative innovation. So it's keeping defects out of our systems. So it's harder to see where that advantage is coming into play. So opportunities to improve this. Those who are promoting model-based systems engineering need to highlight the and promote an understanding of life cycle costs and highlight the fact that yes, there is that upfront cost, but that is made up later on. And further developing open source solutions for model-based systems engineering to perhaps bring down that initial spike, and improving design quality metrics so we can actually see the benefits that come from model-based systems engineering. So compatibility, the current perception is that MBSE is new and different, and that we can't really see the specific need that MBSE fills. So we need to recognize and promote and make sure people understand that MBSE isn't a buzzword. It's not a new thing. It is systems engineering fundamentally, using models instead of documents. A way that we can make it more compatible with existing mental models is to tailor an MBSE methodology to existing systems engineering processes for a particular organization, and focusing again on the needs that MBSE meets. The need in a system to enforce consistency between systems engineering artifacts, to reduce errors that are introduced, and to serve as an authoritative source of truth for systems engineering data. Complexity is a degree to which an innovation is perceived. So MBSE, how does that fall in? Well, it is highly complex, or can be perceived as highly complex, in that you're talking about new language, tools, and processes. For systems engineers that are used to working in Excel and Word, Visio, standard productivity tools, it can appear to be highly complex. So ways that we can reduce that is by making sure that whenever we introduce MBSE, that we have a clear modeling purpose. Recognize that we're not doing MBSE just to do MBSE. And that clear modeling purpose will provide context for those involved in the MBSE effort. And if they have context, they can see more clearly from the diagrams what you're trying to convey, and that can reduce the complexity. Also, having established roles where not everyone on a systems engineering team needs to be an expert in the modeling tool. Most people just need to know how to read a diagram. And if we establish those roles, we can tailor the training and not overwhelm people with things that they really don't need to know, and further reduce the complexity in that way. So trialability, the perception is that MBSE is all or nothing, like I'm doing it or I'm not. And again, we have that high cost of entry that hurts our ability to try it out. So the opportunities there is in doing pilot projects, recognizing that you can do MBSE for as big or little part of your system as you want. And a system model is complete as soon as it answers the question that you set out to answer with that model. So if you just want to do a single mission thread or a single capability, model that, and you've done MBSE for that thread, and you can see the value early on and try it out. And again, as we further develop open source solutions to doing MBSE, it will give more opportunities for groups and individuals to try it out. And one of the big ones is there are wonderful tools out there, and vendors have a vested interest in helping us to learn how to use them. So if we utilize tool vendor trial licenses and training, that can help get an organization off the ground. Finally, observability. It's just really hard to see the problems that are prevented. Going to MBSE, we never mean to put defects into a system. We can just think, hey, we suddenly got better at systems engineering, and we're not seeing or have the ability to attribute those benefits to model-based systems engineering. So the opportunities that we have to improve there is to conduct design reviews directly from the tool so that stakeholders can see the times that consistency is enforced by using it, when ambiguity is removed. They can see the benefits of object-oriented principles like modularity, encapsulation, inheritance, reuse, those types of things, and be able to show people the benefits. And again, improving design quality metrics so that we can point and say, here is how MBSE helps. Again, in the literature, it's been shown that MBSE can reduce project development costs and reduce system defect density while improving on-time delivery and the probability of a project success. So there truly are those benefits. We just need to make those more observable to potential adopters. So I've moved really fast through the introduction, but this is where I'm at with my research. Now where I go from here is actually doing a structured study to determine how MBSE would be evaluated with respect to these attributes that I talked to in organizations that have already successfully adopted MBSE, those who've tried to adopt it and failed, or those who are considering, and see if there's a correlation between how they evaluate MBSE with respect to these attributes and their success in adopting it. From there, I'd like to use the results of this study to inform a way forward to better shape how MBSE is perceived by those organizations to help speed up that adoption rate. And finally, I would like to investigate the other variables, just because some innovations are mostly explained by the perceived attributes of innovation or perceived attributes of the innovation. I'd like to still go back and explore, what effect does the type of innovation decision and the communication channels, nature of the social system, and extent of the change agents promotion efforts, like what effect do those really have on the adoption rate? So that's it. At the end of the day, I'm a firm believer in the benefits of model-based systems engineering, and there's been so much good work done in developing and promoting that practice. So I would like to bring in the diffusion of innovations theory to help us accelerate the adoption so that the benefits of model-based systems engineering can be realized more widely. And with that, I know I kind of took a lot of the time, but if there's any questions, I'd be happy to take those now.
Yeah, I have a question. This is Mac. I think we're doing, in some regards, pretty similar efforts. How does one model and characterize quantitatively, well, this is how something was done, here are some of the success metrics, and if we were to implement MBSE, how can we model that, and how can we, I guess, prove that if we had done MBSE, we could have reduced these shortages and yeah.
So that is a great question, right? Because you typically aren't running parallel, right? You're doing document-based and model-based at the same time, so you don't have an apples-to-apples comparison. There have been some organizations that have published results where there actually is one in particular that did both in parallel, and they were able to show that the model-based approach actually did reduce the defects. A lot of it comes down to using historical data for an organization. So we need to use that historical data to compare it to the new programs that are using MBSE, or like we said with the pilot projects, develop these metrics, keep doing the bulk of your effort in the document-based approach like normal, but on this pilot project, capture the same metrics so that we can look at them side by side. But you're right, that is a great point, and the challenge is, you got to go, you have to invest your effort somewhere, and so it's hard to get that direct apples to apples comparison of model-based systems engineering is in fact better than document-based.
Hey, this is Vincel. Bishop, I had just something real quick because I see time is running out. And it's not so much really a question, but just like an idea I wanted to throw out there. Have you thought about measuring like time gaps and contribution during the model-based systems engineering process, like when you've got, all of these systems engineers making changes to the tools and the models, like measuring, okay, how often did they make change? How large were the changes, and measuring the cadence of those changes, and maybe it would be useful to detect, hey, there's kind of a lull in design, or there's, some pace of change, was interrupted or something. And I just wanted to throw that idea out there, that I think it would be, interesting.
Yeah, that's not something that I had, considered in part of my research, but that is a great point, and something that would be interesting to look into, because one of the fundamental value propositions of MBSE is when you make that change, it's automatically and instantly propagated, throughout the system model, any place where that change would affect your system model. And so if you can quantify, in the document-based approach, how long is it taking changes to propagate to, to all the different disciplines and all the different artifacts, and compare that to the instantaneous propagation through MBSE, that would be interesting. But so far, it's not something that I've included, but it's something that I, could consider to see if it fits in with my primary research goals.
Yeah, and
Yeah,
the legacy data on that change, like change to the legacy system, probably exists.
Yeah, absolutely.
Review and approval boards, right?
Yeah.
well, my research involves doing that same type of analysis, but for software development. And so you can kind of imagine how that would look. But, like treating the MBSE process and making changes to the model as software development. So yeah, stop there.
No, great point. I appreciate that.
Awesome. Well, thank you all. We are at time now. But if you do have follow-up questions for any of the presenters and can't find their contact info, we can definitely get you connected. Thank you to everyone who presented, and we'll see you all in, I think, 2 weeks for day 2 of these presentations. So thank you, and have a great rest of your Friday.
Fantastic.
Thanks.